All right, let's jump right in. We're going to talk about one of the most fundamental tasks in all of data science, finding the average. I know, it sounds almost too simple, right? It's like the first thing you learn in Statistics 101. But what happens when that simple task gets, well, really, really complicated?
See, this is the real question, because in the real world, data is messy. It's not clean. Sometimes your data has outliers, these rogue points that are so far off from everything else they can drag your average way off course. You can almost think of them as liars in your data set. So the challenge isn't just about finding an average, it's about finding the true average, even when some of your data is actively trying to throw you off.
And what's super interesting is that these so-called liars really come in two main flavors. On one hand, you've got what are called malicious corruptions. You can think of this like an actual cyber attack, where someone is intentionally poisoning your data to mess up your results. But on the other hand, you have something called heavy-tailed data. Now here, the outliers aren't evil, they're just extreme. They're rare, but totally legitimate values that can happen naturally in the world, like in stock market fluctuations or internet traffic.
So for the longest time, researchers basically treated these two problems, the malicious outliers and the natural ones, as totally separate issues. You had computer scientists working on one and statisticians working on the other, and they each developed their own unique toolkits. It was kind of like two groups of doctors trying to cure a similar disease without ever talking to each other.
And the solutions they came up with were, honestly, incredibly complex. They were highly specialized, often what we'd call ad hoc, meaning they were custom-built for one specific type of problem and didn't work for the other. As the paper we're looking at puts it, the connection between these two worlds was murky. Nobody had a big-picture unified theory for handling outliers, no matter where they came from.
And this whole messy situation led the researchers to ask two really big fundamental questions. First, hey, are these two problems secretly the same thing? Is there some deep, formal link between handling malicious data and handling naturally extreme data? And second, is there a simpler, more elegant way to understand the algorithms that solve them, instead of just building these one-off, complicated mathematical proofs every single time? And this, right here, is where the breakthrough happens. The researchers behind this paper found a way to boil down both of these seemingly separate challenges into one single, powerful meta-problem that connects everything. They call it spectral sample reweighing. Now, I know, that sounds a little intimidating, but the core idea is actually super intuitive. Instead of just finding the outliers and throwing them away, the idea is to just reduce their influence. You give every single data point a weight, and the goal is to find a center, a mean, that makes the whole cloud of points as round and spherical as possible. You're basically trying to find a center that makes the data look uniform in all directions.
And this slide just perfectly shows you how it works. So you start with your data, and because of outliers, it might be stretched out, looking more like an oval than a circle. The algorithm is smart enough to find the direction of that stretch. Then it just systematically dials down the importance, the weight, of the points that are pulling it in that direction. You do this over and over, and piece by piece, that stretched out data cloud gets gently squeezed back into a nice, compact sphere. And the center of that sphere? That's your true, robust average.
But the paper didn't just stop there. They found something even deeper, a kind of hidden secret they call a duality. And this is what formally proves why this one simple idea works for both of those old, separate problems. It all comes down to a really basic question. What does it even mean for a point to be the center of a whole bunch of other points, especially when you're dealing with data in hundreds or thousands of dimensions? Well, it turns out there were two very different answers to that question floating around in the research world.
On one side, you have the spectral center. We just met this one. It's that geometric idea, the one that tries to make the data cloud as spherical as possible. On the other side, you have the combinatorial center. This is a totally different way of thinking. It's a counting property. It basically says a point is a good center if no matter which direction you look at the data from, no matter how you project it onto a 1D line, a clear majority of the points land close to your center. One is about the overall shape, the other is about counting majorities in every possible direction. And here is the real kicker. The paper proves that these two completely different ways of defining a center are actually the exact same thing. They are just two sides of the same coin. Finding a point that makes your data geometrically spherical is the same as finding a point that has a majority of data nearby in every single direction. This was the mind-blowing insight, the missing link that finally, formally unified these two fields.
Okay, so they unified the theory, which is huge. But remember that second big question?
Could they find a simpler way to analyze these algorithms? Well, the answer was yes, and it involved borrowing a clever tool from a completely different part of computer science.
You have to understand, before this paper, proving that one of these outlier fighting algorithms actually worked was a nightmare. It required, as the paper says, significant creativity, which is code for it was really, really hard. You basically had to invent custom math from scratch for every single algorithm.
The author's brilliant idea was to reframe the whole thing. They realized this process of iteratively reweighing data points looks a whole lot like a classic problem from a field called online learning. And guess what? That field already has powerful off-the-shelf tools for this kind of analysis, specifically something called regret bounds. By looking at the problem through this new lens, all that complicated, custom-built math just disappeared.
In this table just lays it out so clearly. Look at the difference. For one algorithm, you go from building these complex potential functions by hand to just plugging in a standard regret bound. For another method, you go from needing all these sophisticated non-convex optimization tools to, you guessed it, just using that same standard regret bound. The result? The proofs become way simpler, and as we're about to see, the algorithms actually get better. So let's make this real. What does a simpler proof actually get you? Well, look at this. The old analyses could only prove that an algorithm would take a number of steps that grew incredibly fast. In this formula, n is your number of data points, and d is the number of dimensions. The scary parts are the exponents, n squared and d to the fourth power. This just means that if your data gets a little bit bigger, the time it takes to get an answer absolutely explodes. It just doesn't scale.
But with their new, simpler analysis, look at this! The new runtime is so much better. The number of steps now just grows linearly with n and with d squared. We went from d to the fourth to d squared. This is a massive, massive practical improvement. It's a perfect example of how a deeper, simpler understanding of a problem can lead directly to building faster, more efficient tools.
So let's step back for a second and just take in the big picture. Why does all of this matter? What's the real power of having this new, unified view?
It really comes down to these four things. First, unification. This paper built a bridge between two fields that had been separate for decades. Second, simplicity. It gave us a clean, principled way to analyze these super complex algorithms. Third, that simplicity led directly to better performance, giving us faster, more practical tools. And finally, it gave us this incredible insight into the deep nature of data itself, revealing this hidden connection between its geometric shape and its counting properties.
You know, this whole journey started with a simple problem, finding the average, and ended up uncovering this beautiful hidden unity in a really complex part of statistics. And that kind of leaves you with a final thought, doesn't it? What other messy, complicated problems out there in science and technology are just waiting for the right perspective, for that one simple unifying idea that suddenly makes everything clear?